Hello everyone again. We are pleased to introduce the Dr. Daniel Sierra Sosa, Assistant Professor at the Catholic University of America, who will present the topic Quantum Machine Learning in the Utility Era. In recent years, there has been massive progress in the development of quantum technologies. Research on real-world application for quantum device has become a central focus within quantum computing, a field that integrates theoretical physics, engineering, software development, and education. One area of active investigation by several research groups is leveraging the unique advantage of quantum computing to advance machine learning. Ongoing efforts include developing quantum version of both supervised and unsupervised techniques, such as artificial neural networks, clustering algorithms, Gaussian models, vector quantization, and principal component analysis. In this talk, we will explore the implementation of quantum machine learning techniques on real-world datasets, considering the practical limitations of current quantum hardware, including the restricted number of qubits and their susceptibility to the noise. By the way, Dr. Sierra's seasons will be the last one for today. Dr. Sierra, can you hear me?
Yeah, I can hear you.
Ah, te. Uh, One more thing, I would like to mention that you have the option to present it in English or Spanish, wherever you prefer. Uh,
Oh,
can
thank you.
you start, Dr. Sierra?
All right, thank you very much. Let me share my screen and thank you very much for the introduction. And thank you very much for inviting me to participate in this version of the Qiskit Fall Fest. I've seen the program that you have, and there are many talks that are quite interesting. Some of them are in quantum machine learning. This will be yet another talk on quantum machine learning, but we are going to basically evaluate or talk a little bit about what are we going to need to do quantum machine learning, but not like in the future, but what we need to what we can do today with this technology. So the first thing that I want to share with you is that any machine learning algorithm, either classical or quantum, is going to be a data-centric algorithm, meaning that data is the motor that is going to actually allow us to understand how we are going to produce these techniques and methods that are going to allow us to obtain a particular output. For example, if we want to do classification, we are going to need to have the different groups or subsets of data that are going to be well defined, and they are going to have certain properties that are going to connect them together in order to be able to do that classification. If we want to do forecast, we will need enough data in order to actually know the general rule that we are going to try to get in order to produce that forecast that we need. And this will happen with every single data set that we assess. And something that we need to take into account is that here we have four possibilities. And I'm pretty sure that you have seen this graph in many presentations, in many books, in many research papers. And you have seen this graph so much because it's quite eloquent when it's telling us what are the possibilities that we have in order to assess the information that we want to process. So on one hand, we are going to have the classical data, and in other part, we are going to have the quantum data, the classical data, quantum data. We are going to have the classical processing and the quantum processing, and how we combine this is going to actually produce the different approaches that we are going to take. So we are really used to work on classical machine learning, where we are going to have classical data and we are going to process that classical data with classical devices, and we are going to be able to produce our neural networks, clustering algorithms, PCAs, support vector machines, so on and so forth. that are super efficient and actually having us in this AI boom that we are living today. So on this premise, what we have today is a really, really efficient way in which we can process information in order to produce an outcome. But now, with the advent of quantum devices, we are going to have the possibility of processing information in a different way, and is that we are going to be able to produce a different type of algorithms and different type to approach to problems that are going to allow us to see and understand this data and the world that it's representing in a different way. And this opens the possibility to hybrid algorithms where we are going to be using classical data and we are going to be able to process that on a quantum device, or we are going to have quantum data and we are going to be able to process it on quantum devices in the same way, right? So with this, we have many possibilities, but something that we need to take into account at least today is that these techniques that we are creating in quantum machine learning are going to be highly, highly unlikely that are going to beat the classical machine learning in terms of performance for classical data. Why we are given this warning? This warning comes from several aspects. So when you create a machine learning algorithm, you want that machine learning algorithm to be useful and to serve a particular purpose that you have. So think that you are the owner of a company, and being the owner of a company, you have been collecting data for a certain amount of time, and you are going to hire a company, yet another company, a third party company that is going to do the processing for your data for producing a machine learning algorithm. If that is the case, then you're going to be presented with two options. One is going to create an algorithm that is going to be based on cloud computing for classical data, and the other one is going to be quantum computing processing your classical data. When you are in this position, you will need to think in several things. What will be the performance of the algorithms that we are implementing? How efficient this is going to be for running these algorithms on the data that I have. And one that is crucial, especially if you are the one paying, is how much it will cost me to actually process this information. Uh, Again, you will need to assess how much time it's going to take. But with these conditions, um, nowadays, the algorithms that we have in machine learning are extremely proficient for processing classical information. But there is one good news here, and is that if we think in a set of problems that are going to be a particular set of problems, we could find that the use of quantum devices could improve or could make the evaluation of this information feasible. And in this event, you have a couple of talks that go over those examples. In this one, we are going to just basically cover an overview of all these techniques and how we can approach these techniques in a way that we are going to be able to understand what we are doing. So I'm going to be talking about some general aspects of quantum machine learning in today era, the utility era. And we are going to see what are the conditions that we will need to take into consideration when we are either training or testing this particular model. So the first thing is that we will need to produce an algorithm that is going to learn from data, is going to get certain patterns, and is going to produce the expected output. With this, what we are going to do is we will need to break these algorithms in different pieces. Why? Because we will need to actually start working on having this information process. Again, all these algorithms are going to be data-centric, and in that sense, we are going to start with classical data that comes from the real world and are from applications, and we will need to process and prepare that information in order to be able to be processed by a quantum device. And this is going to be the first of our step, the state preparation. In the step preparation, we are going to have different considerations. We are going to go over some of those considerations, but in general, the idea is that you want to create a one-on-one mapping from classical data to an actual quantum state that lives in the Hilbert space and comply with certain conditions that you will need to have there, right? Once you have the data prepared, you're going to be able to produce your model that could be either pure quantum model or a hybrid model that is going to contain a classical part. And then with this, you're going to have different approaches. For example, you could have variational or parametric quantum circuits, or you could have variational circuits perceived by perceptrons, or any other layers. We are going to see some of those. But the idea is that you're going to create your model either pure quantum or a hybrid of quantum classical. And then you are going to need to produce an optimization of your model based on the information that you have. And with this, you're going to define algorithms that are going to update the parameters of those parametric circuits and are going to induce or evaluate a function, or they are going to actually basically measure how far the data is from each other. So with this, we have three approaches here that we are going to be considering. Again, this is not an exhaustive list, and some could argue that there exist other techniques and other methodologies that are not described by this precise graph. That is true, but this in general will cover most of the applications that we are going to have, and some of those applications that don't completely fall inside this graph are going to be applications that are likely modifications of what we have here. So on one hand, we are going to have feature encoding and variation on algorithms. Here we are going to have techniques like the BQC and others. We are going to have another type of or family of techniques that are going to be the quantum kernel techniques, where basically what we are taking into advantage here is the fact that we can compute inner products. I mean, quite efficiently on quantum devices, and with this, we'll need to define a circuit that will actually allow us to calculate those kernels. And then we are going to have another approaches where we are going to be in the realm of the quantum neural networks. That is going to be the data re-uploading circuits, where basically we are going to have different layers that are going to intertwine in different ways the data that you have as quantum state with variational approach that could have different type of parameters, and then at the end you're going to evaluate a loss function that you're going to be processing, right? With this, notice that something really interesting is that we have a new way in which we are going to be able to process information, and with this we are going to have three important things that are going to be the main idea of why we want to do quantum machine learning. And this is up to some extent my view on this. Some could disagree, but I think that we have three main components that are going to be our driver and our motivation for working and trying to explore quantum machine learning, right? The first is a challenge, an opportunity, and a promise. The challenge is that we don't need to assume anything from the data, because we cannot guarantee that any data set is going to behave like other. But basically what we want to do is we have an input, and this input is going to have no particular mathematical structure. Is going to be anything that it's going to be given by the experiment that you are creating. And with this data, with this structure that you have, you will need to actually create a mapping schema to embed the data into a pointer to the Hilbert space. And then you will need to do this in a smart way. What is a smart way? One way in which you're going to be able to efficiently map your data into this Hilbert space, and that they are not going to have any clashes between data. That is going to be a one-on-one mapping. And also, I said like efficiently 10 million times, but once more is important. It needs to be efficient, because if you spend a lot of time or you have a really complex algorithm for mapping your data, then the advantage of doing QML is going to be basically pointless, because by doing the translation of the data as a quantum state, you actually start losing against classical machine learning. So that's the challenge, how we are going to be able to embed the data as a quantum state. The opportunity that we have is exactly something derived from the challenge, and is that we have actually the freedom to choose an embedding map. And with this, we are going to be able to design different and diverse algorithms that are going to allow us to define the data in a different way. And we are going to see those classical examples, well, now classical examples that we have seen in several presentations and in several textbooks. But the reality of this is that now that we need to embed the data, how we are going to profit from that embedding in order to help us solve the problem that we have in our hands. And the promise is naturally that the quantum machine learning for certain problems is going to either accelerate the task that we want to do, or is going to actually make them more efficient. With this, what we have is the whole picture on why we should do, at least in my opinion, quantum machine learning, because based on this schema, we are going to be able to process certain type of information in certain ways. So one thing, and this is really important, is that when we started working, and when I say we, I said as humanity, when we started working in machine learning, we were super careful about doing good feature engineering and create algorithms that were custom made for the actual data that we had. And in just a couple of layers, we were able to create algorithms that produce classification, that produce forecasts, and that produces all this good stuff that we have from the machine learning. But then computers start to become more and more powerful. And what we did is we started to collect more and more data, paying less attention to the good processing of information, and trying to solve with algorithms that are more complicated, more robust, and with more data, solutions that could be approached on a simpler manner. In quantum machine learning, these problems are fully data centric, and then we will need to go back to that era where we were taking good care of the data, we were evaluating the properties that we need, and we create an algorithm that is actually custom made for processing that information. And with this, if you start experimenting on quantum machine learning, you're going to realize that, for example, you could create your wonderful variational quantum classifier for a particular data set. And when you change the data set, this algorithm that was working for that particular data set is not going to work anymore. And with this, we have to think in this direction. Not because you have a hammer, all your problems are going to be nails. And with this, we will need to start working one-on-one on the problems that we have. So let's start by talking then about the quantum embeddings. So what we are going to do is we are going to take our data, and the data is going to be the classical input, right? Once we have this data, what we want to do is create an encoding schema that is going to take us from the classical representation of data that lives in the real numbers to an encoding schema for numbers that could or could not, depending on how you design your algorithm, live in the complex numbers and live inside the Hilbert space. What you will need to guarantee is that any schema that you create for embedding is going to end up in a unitary matrix that could be described as a quantum state, right? Once you have that, you're going to actually produce your algorithm. You're going to read it. Notice that in reading, we are going to have also some nuances that are going to allow us to produce different type of information. And then we are going to get, let's say, the prediction. But as we are saying prediction, it could be forecast, it could be whatever you want. Now, in this schema, what we want to achieve, and when I say this schema, I'm referring to the encoding. What we want to achieve is we want to actually create state preparations that allow us to simplify, or at least make easier to process the data that we have, and that we are going to be able to profit from it. So this is what we are doing. Now, what we will need to do? Well, basically, what we are aiming here is that we are taking data that is going to come in a space X that is going to have whatever number of dimensions, and we are going to take this to the Hilbert space, right? Where basically what we are doing is we are creating from an initial state an evolution of that state that is going to be depending on the information that we have for that data in order to modify that. And with this, we will need to create embedding systems that are going to be optimized for whatever task. In this case, I decided to go with classification because that is the one that we can understand intuitively, and that we can see that, okay, if this data needs to be different from this one, this is a good schema for us to assess. And there are going to be many ways of doing this mapping and this embedding, right? Let's give it a small look about what we are pursuing here. So we have a quantum state. And in a quantum state, we are going to have obviously larger bases, but these two bases that I'm taking as an example from the book from Maria Schula and Francesco Petrucciani is going to be good enough for describe the problem. So when we have the quantum state, we are going to have different elements that are going to be useful for encoding data. So the first schema that we are going to follow is we are going to encode in the bases. Here is the one that is the most classical approach, or the most classical way of thinking for the encoding, where basically we are going to start with 0, 0, 0, 1, 1, 0, and 1, 1. And for any data point that we are going to have, we are going to create this bit string that is going to apply NOT gates into the particular qubits that we are interested, and we are going to be able to process the information in this way. What is the price to pay here? That you are going to need many, many qubits for representing many numbers. Or if you want to see it in another way, which is also is the same, but it's a different approach, is that you will need to have many qubits to have good resolution. So you're able to define between 2 points, right? So let's say that this is going to be easy to compute, but it's not going to be efficient in terms of the amount of qubits that you're going to use. Other option that we have could be, for example, encoding into the amplitudes. Here, what we are going to do is we are going to transform our data in a way that we are going to be able to map it into the different amplitudes that we have for the data. Other way that we have for encoding the information could be, for example, defining a Hamiltonian that is going to be a matrix that is going to depend on the data that you have. Other way of encoding information would be as a time evolution. And for example, here you're going to be able to solve problems like lattices and whatnot. But the idea is that you have many options for encoding information. And with this, you're going to have many opportunities for getting different type of outcomes out of the information that you are creating, right? So let's start. This is based on the data. Now we have seen that we need to encode the data. Naturally, we haven't go into the detail of how to encode this data. And then let's talk about the machine that is going to produce our algorithm. And this one is going to be the parameterized circuit. In the parameterized circuit, what we are going to have is we are going to have one piece of the circuit that is going to process our information, one piece of the circuit that is going to be the variational approach. We are going to change this based on measurements that we do on the circuit. We are going to change this based on the data that we have, and basically this is going to be the part that is going to have our optimization schema, not the optimization per se, but it's going to be the target of the optimization that we have for the circuit. And then we are going to have the measurement. And notice that when we are working on quantum devices, this measurement is not unique. You could do projections on different axes. You could do different type of measurements that are going to give you different type of answers. And we are going to explore that a little bit further when we are seeing a small example that I prepared, right? So we are going to have our parameterized circuit that is going to be based on the data. What we want to do is we want to take our information, create an operation that does the embedding, and we are going to end up defining that data into the number of qubits that we have. That is going to be our Hamiltonian, right? So what we want to do is we want to create some information that has a good expressibility of the data, so we end up with many possibilities. What I'm saying here is that there are going to be different ways as you have different ways in which you can encode the data. you're going to have different performance for those encodings. You want to have one that is expressible enough, but you don't want it to be as random as you cannot determine or define anything out of it. So with this, we are creating the encoding. What we are looking with it, well, let's give it a look to the feature maps. When you have, for example, data, and you are mapping the data, you could do it, for example, taking advantage of this change of basis you're doing. And you could do it, for example, for a high dimensional. If you do that, it could make classification easier, or it could get a better representation of the information that you have, right? So this information that was originally taken from the original data could be transformed by means of a function that is actually increasing the dimensionality of the data and is being operated over different points of the information that you have. So notice that we started in 2 dimensions, we end up in 3 dimensions, and these are going to be based on a function. So when we do this, we are going to have different type of classes. Let's go back to classification, and then we will need to measure, right? So if we want to measure how similar are the yellow points within each other, how similar are the purple points within each other, and this is basically creating a metric where we are going to have a function that is going to tell us how far apart in terms of the metrics that we are evaluating are going to be the points from one group and the other. Notice that if we do this, basically what we can say is, hey, for the transform domain that I'm creating in my feature maps, I could also have a measure of similarity because it's going to be the difference between the evaluation of that feature map that I created. Going further, this measurement could take advantage of something. And that something is, let's say, and with this, we start with a particular example. Let's say that we want to calculate the inner product, right? Why is that? Because we want to define a function that allows us to say how different or how likely 2 points between each other are. And then this is where we need to start thinking in the benefits of using a quantum device. And one of the things that we can do with certain simplicity on a quantum device is actually calculating inner products, right? So we can say how close 2 points are by calculating this inner product. And with this, we can start thinking, for example, in variational algorithms. We can start thinking in support vector machines. We can start thinking in different ways in which we are going to actually start measuring this similarity in order to get the outcome that we are expecting, right? One thing that it's really, really important is that we want to map information in a way that make our life easier, right? So we want to, for example, change this data that we have here between -2 and 2 to a representation that is actually in the Hilbert space, but it doesn't make our task more complicated, right? So with this, what we can do is, let's say that we can start adding the encoding of the data and the variational part. Assume that this is one block, and then we can train. We are going to measure, we are going to evaluate the distance that we have for our feature map. We are going to end up with a cost function for in this case classification, or whatever you want, but it's going to be classical anyway. And with this, we are going to fit our algorithm, and we are going to start running this over and over again until we find the output that we get. Notice that something to take into consideration, and this is for today. Uh, Training a machine learning algorithm on a quantum device, in my opinion, is a big no. Why is a big no? Because it's going to be extremely, extremely expensive. So, for example, if you are doing it for academic purpose and you have a really small data set where a couple of points where you want to tune stuff, that is good. But think if, for example, you want to solve a real world problem where you have multiple data points and where you're going to need to assess a lot of information, with today cost of quantum computing, it's unrealistic, uh, in my opinion, thinking that we are going to be able to train a model, deploy the model, and have it running, right? We need to think in strategies that allow us to use these techniques in an efficient way nowadays. One of those options, for example, training on a simulator if the dimensionality of the problem allow it, and then the results that you are getting, you can do the inference with error corrected error mitigation algorithms on a real device. Stuff like that is something that we can think about, right? Let us explore two techniques. One is the quantum support vector machine, where basically we are going to evaluate how far or how close the data points that we have between, let's say, two different subsets inside your data are going to be from a hyperplane that is going to divide them, right? So the idea is that you want to find that hyperplane that is going to maximize the margin or the distance that you're going to have between your data and the classes that you have. When we are thinking it this way, this is the classical approach, we can start thinking into creating something that is going to be more oriented to quantum computing. And that will be the case of the quantum support vector machine, where basically our kernel function is going to be defined by evaluating the inner product that we have between the data points, and with this we are going to see how similar they are. So this is one option. Another option could be, for example, working on variational algorithms, where we are going to introduce different variational forms to try to solve the problem. And when I say to try, it's that these variational forms will depend on what you want to achieve and the data that you have and the relations that you have between the different data points that you have. We are going to follow more or less a similar schema that we have before, but what we are going to do in this scenario is that we are going to update the parameters that we have by means of the optimizer of the variational circuit. So once we have the data and we pre-process the information in order to transform it into a feature map, we are going to have this variational form that we are going to start updating based on what we have. So what is the trick? We are going to have a quantum device that is going to receive the parameters for these variational forms, and we are going to be evaluating on a classical device what are going to be the outputs that we are taking, and then we will need to rerun this. So notice that based on the feature map that you have and based on the variational forms, you will need to run multiple times when training an algorithm, and this is what make it, based on the cost that we have today, not really feasible for having a training on real devices today. Um, when we are talking about these variational forms, we will need to actually create models that are going to be data-centric. And this is where we are going to start introducing other type of variational forms that we are going to use for better represent the data. One of those ideas being currently researched and explored is the use of tensor networks, where basically what we are going to do is we are going to represent the circuits as networks of tensors that are going to be connected with each other, and where we are going to have a bonding dimension between the different nodes that we have in order to create those circuits. And we are going to see a couple of examples. So just to start from the beginning, a tensor is going to be a multi-dimensional array that is going to allow you to represent different numbers in different dimensions in an intuitive manner. So the idea is that you are going to have a schema for generalize all the information that you can collect. But we are going to be using just one simple notion, yet really powerful, that is the tensor contraction, and is that when you have two or more tensors, you can contract them by adding repeated indices, and with this you're going to create the contraction. So if we want to see it this way, we are going to have two tensors A and B, and we are going to have one bonding dimension that is the one that is going to be related with the repeated index that we have. If that is true, what we can say is that we can evaluate any product C that is going to be the multiplications of the tensor A and B as the sum of different indices that we are going to have for rows and columns based on the bonding dimension that we have. This is going to allow us to create structures like this, where basically we are going to be able to transform these tensor networks into actual quantum circuits that are going to allow us to process the information in different way and are going to allow us to create a better representation of the information that we have, right? So with this, we are going to be able to have a better processing of the information. And then we are going to have different schemas for processing the information. We could have, for example, perceptron models, where basically we are going to have our data and our weights. We are going to operate over that. We are going to create one circuit that will act as the activation function of this perceptron. We are going to evaluate the function that we are interested in terms of the weights and the values that we have. Or we could have neural networks where basically we are going to re-inject the data and different variational layers to evaluate a loss function that is going to actually update the information that we have. Or we could create schemas of circuits that are going to act as convolutional neural networks, where we are going to have our convolutional layers and our pooling layers dropping some of the information. Or we could have something like the dissipative quantum neural networks that are going to be a way of implementing fed-forward networks. Notice that with this, what we are doing is that we are creating different approaches by using quantum circuits to process the information. But what is the most important thing is the information here, right? Um, just to finalize this talk, I will share with you one case study, and I am going to share a case study that is based on the healthcare problems, right? And we are going to talk about the ischemic heart disease. So basically, in the ischemic heart disease, what you are going to have is that the vessels and your veins are going to be starting to get blocked, and the blood is not going to pass as easy. So you're going to have this narrowing into your blood vessels, and this is going to start damaging the heart or the blood vessels themselves. And then you're going to start having other conditions. This problem is relevant because it's one of the main causes of death in the population. And another thing that makes this disease so relevant is that some people could have, let's say, myocardial ischemia and have no sign or symptoms whatsoever about this disease. So the tracking and that we can do on our heart condition is going to be really relevant. The other thing why we want to work on this is because cardiology has a ton of technology, because there are so many people suffering from cardiac disease. There are a lot of technology used for cardiovascular problems. And then we are going to have a lot of data and a lot of information with many techniques that we can use as benchmark for our quantum model. So one thing that we want to pursue here with this particular case study is understanding a little bit about the feasibility and the performance of the quantum machine learning techniques compared with those that are classic, right? And we are going to use an open data set for this one. We are going to take the data from the IEEE data port. And basically, what we are going to have here is 5 independent sets that are going to come from 5 different hospitals. And we are going to have 11 common features for 1,190 records, where basically what we are going to do is we are going to do classification between ischemic heart disease or not. What is going to be our value 0? We have less than 50% of diameter narrowing. Value 1, meaning that we have ischemic heart disease, is going to be larger than 50% narrowing in your veins, right? And the data that we are going to consider are going to be the age, the gender, the type of pain in the chest, if the patient's presented some time of pain. We are going to have the resting blood pressure, the cholesterol, the LDL level. We are going to have fasting blood sugar, resting electrocardiogram, what are going to be like the evaluation of those resting electrocardiograms, abnormal, normal, or not present. Then we are going to have the maximum heart rate achieved. We are going to have exercise-induced angina. We are going to have the PICA-ST that talks about the maximum ST depression, that is a segment into the electrocardiogram, where we are going to basically see what is the distance that we have between the baseline's reading and peak exercise reading. We are going to have the slope, how fast you reach that peak. And we are going to have finally the diagnostic ischemic or not ischemic heart disease. And what I want to what I want to show you is that we are going to have the possibility of producing different type of algorithms. So I created a set of classical algorithms: the support vector machine, name base, logistic regression, decision tree, random forest, XGBoost. And with this, I said, okay, I got, and I have all the rest of the metrics here, as you can see, but let us stay with the accuracy for the sake of comparison. And basically, what I'm getting is that without a lot of tuning, and this is something that we can discuss, without a lot of tuning, we have a classification that peaks at 88%, right? And the lowest one that is going to be the naive Bayes or the logistic regression are going to be in 78%. 2% is not a big difference. That is in the margin of error for these techniques. But then we are going to run a quantum super vector machine and a variational quantum classifier. Both of them are giving us 77 and 73%. Again, this is just a case study to assess the feasibility. The results are not great, but it shows us that with these quantum techniques, we have the possibility to reach those accuracies that are comparable with the ones that we get from classical techniques. It's important because these are the first steps that we can start making in order to get the use of these techniques, right? And we can make this a little bit more complicated. We could use different tensor networks, the MPS or the TTN that we are going to have there. And notice that with these techniques, we don't reach a lot better performance for the model, but we are in the neighborhood of the model. Now, some comments that I want to make here about this particular example is that, yes, you can improve these results by much. This is just a case study for assessing that we can run and obtain results. And then I have not compared the quantum machine learning techniques with those that are most advanced right now. For example, we could have done a deep neural network or something more robust that probably are going to end up with better classification, but it's just to have a fair comparison between the techniques that we have today. All right, so on um, I, I will open I will be open for questions in just 1 second. There is something that I want to share with you, and is how you can do a variational quantum classifier by using IBM Qiskit. This is just a toy for us to play, but I believe that having this hands-on approach is really important for actually understanding the current limitations and the difficulties of doing quantum machine learning that go beyond what we do in research. So I will share this with the organizer of the event, so you can ask them if you want for this code. So the idea that we are going to do is we are going to create a synthetic classifier, variational quantum classifier, and we are going to explore each of the different components that we have. We are going to have the feature map creation, the variational circuit, we are going to perform the measurement, and we are going to use a classical optimizer. This part is not is used from a library, but you get the idea, right? So first of all, we are going to start with a classical data set. We are going to use make blobs, and we are going to reduce it to 4 dimensions with 2 classes. And notice that with this standard deviation that we have here, 0.1, if we do a projective graph of the data, is going to be highly separated. We are going to split the data into train and testing subsets, and we are going to start creating the circuit separation. The first thing that we are going to use is we are going to create the data encoding. And for that, we are going to use CC feature maps, where we are going to create relations with C poly operations for each of the data points that we have and the connections between them. This is the first part that we have here. Notice that what we are doing here is that we are preparing one circuit per each of the data points that we have, and we are creating the feature map. Then we are going to create 4 repetitions of real amplitudes, a variational form. We could have many variational forms that you are going to be able to create. And at the end, we are going to measure. Now, this is where the tricks start to happen. The first thing is that loading the data into this parametric circuits is going to be up to some extent trivial, because basically we are going to start creating these parameters for the feature maps, and then the parameters that we got from the optimization circuit are going to be embedded into this variational form. But then we will need to actually start thinking what we are going to do. When we measure, we are going to measure one of two things. We are going to measure the histogram that we have if we use the sampler, or we are going to measure the expectation values if we are using the estimator. In this particular example, we are going to use the sampler, and notice that with the sampler, you're going to always be able to calculate the expectation value by using the delta Kronecker for calculating the expectations, but we are going to leave it as that. We are going to encode the probabilities based on the bit string dictionaries that we have, and with this we are going to produce the classification. What we are going to do is we are going to run the code, get those bit strings, and calculate the probability for each of those by using this function. We are going to calculate the cross entropy loss from this one. In this case, is going to be binary. And with this, we are going to get the classification that we have. We evaluate the cost function, and with this, we are going to be able to create the classical optimizer. So notice that what we are doing here is that we are optimizing this circuit that we have based on an initial point that in this case is going to be full of zeros, and then I will try to minimize this objective function. That notice that the objective function, what it's doing is bringing the training data, taking the algorithm and executing to calculate the probability that we have. The cost function runs over time. When you run this, you can see how long it takes for running, even if it has 4 qubits. And at the end, you're going to be able to retrieve the parameters that you have from your most optimal circuit, put it into the inference, and you're going to be able to actually create this. So here is the simulator test that we have. It looks really good. It should be 100% because this data is fully separable, but I leave it as this. But I'm also giving you a piece of code for testing using real devices. If you just use this code for inference, you're going to be within the 10 minutes that are provided for free by IBM. And with this, you're going to be able to see what is the effect of using today devices in terms of time waiting for that to run, in terms of the accuracy that you are going to have in the model, and in terms of the output that you are having on your model. Now, that being said, I'm open for questions.
Hi, Dr. Sierra. Okay.
No, go ahead, Arturo.
Have a one question, Sarah G. Science quantum kernels measure similarity through inner products of quantum states. How do we know that what we are capturing comes from the real structure of the data and not just from the way we encoded it into the quantum space?
Um, when you are this is the beauty of this. When you are encoding the data, the encoding needs to come from the data from the original data. So when you are creating an encoding schema, this is going to reflect the information that you have from the data. And notice one thing: changing or mapping the data, if you do it in a systematical way, is going to work, right? So the data is the one that is driven. The embedding and these embeddings, once you process them, are coming from that particular data set.
I have another question. Silvia Lopez Lascano. Do you think that the development of quantum computing could help us not only process information faster, but also better understand the nature of reality and the multi possibility within it?
This is a really beautiful question, and one thing is, notice that the universe and where we are living right now, it's reigned by the laws of quantum mechanics. If that is true, then it should be also true that the processing of information, or information itself, is going to be also ruled by the rules of quantum mechanics. If we manage to create a way to compute and to process data in such a way that we can define it for being processed on a quantum devices, yes, we are going to actually have a better understanding on the data that we are creating. Let me give you just one small example, and it's quantum chemistry. When we are creating or simulating, for example, molecules, notice that we can do that on a classical device. And right now we have techniques that are super efficient for doing certain molecule simulation, those that are small enough. But notice that in the quantum computer, what we have is that these molecules are going to be defined by a wave function. The quantum circuits are defined by a wave function. So if we manage to translate this, it will be a one-on-one translation where you're going to have a model for computation that is going to be fully attached to the physical and chemical phenomenon that you are trying to simulate. And this is what is going to make us understand better the nature. And I think this is happening today, even with the limitations that we have with quantum computers. We have a better way of understanding the world, and we have a better way in which we are seeing the problems in order to solve them.
Thank you, Dr. Sierra. If anyone have another question, can you post in the chat?
Okay, there is another questions. For students and early career researchers in Latin America, what skills or areas of knowledge should they focus on to become competitive in quantum machine learning research globally?
Um, well, when we started working on quantum computing, if you come from computer science, you're missing the physics. If you come from physics, you're missing the computer science. But this is something that you can get. I believe that if you want to have a set of basic skills for being proficient, not only in quantum machine learning but also in machine learning, it's remember that all these algorithms comes from optimization, and they come from math basically. So, for example, just to give you one example of my requirements for taking the quantum machine learning class that we have here at the Catholic University of America, the only requirement that I have is not even introduction to quantum computing, linear algebra. If you know linear algebra, you're going to more or less understand what is going on. Because, for example, if you are able to understand what an eigenvalue is, what an eigenvector is, how you're going to obtain it, then the rest is just a procedure, and you can change those procedures, so you're going to be able to understand what you're doing. So the basic skill, for, in my opinion, for as a student to get, it's linear algebra, and then you learn about programming and physics, but this could come as a hobby, but linear algebra is mandatory.
Thank you so much. Another question. For the Latin America community, which often has limited access to large-scale quantum hardware, and what will be the best ways to start experimenting with quantum machine learning on real-world datasets?
Um, look, this one thing that I love from quantum computing, and I am originally from Colombia, so I do understand the needs and pains from Latin America, is that in quantum computing, all of us have exactly the same free access to these technologies. So right now with IBM, every month you have 10 minutes. This is not going to be good enough for training a data set from real world, but is going to be a good platform for testing what you're doing. And then right now, with a computer can access to those 10 minutes on real hardware, I understand, because we are so many waiting in the queues is super long and whatnot, but it's something that all of us, and all of us is any single country, first world and development countries, have access to it. So the only thing that you need to start working on quantum machine learning and quantum computing in Latin America is wanting to start working on these techniques, because believe me, we have exactly the same access. at this point is the 10 minutes from IBM, and we have the simulators, and there are many tutorials. Something that I know that we are in the Qiskit Fall Fest, but a really, really good resource that you have out there for learning quantum computing is the Penny Lane Codebook. It's really good because you have the theory and you have the code down here, and then you have a good explanation on the next panel. So you kind of start with zero knowledge on it, and you kind of start working. The other one is that IBM has a learning platform where you kind of start from the basic information up to variational circuits, quantum chemistry, and another advanced tutorial. So the resources are out there. Not having access to real hardware is an excuse for start working on it. Because to be honest with you, most of the research that we do, it's on simulators, because no one is going to have $100,000 on a project to spend on training an algorithm.
And this is another question for those one who really interested to jump in the field. And there is any opportunity, to make a thesis with you or inside your group or something related. For those one really want to be big interesting and see, okay, I want to work with Sierra Sosa in a specific project, even doesn't matter that we virtually. There is a chance for them.
Absolutely, yes. I'm working with people from Mexico. I'm working with people from Colombia, with people from Argentina. So sure, just reach out and let's see what we can do. Now, this is not a promise that we are going to work together. When we are doing a thesis, I need to put commitment. You need to put commitment, and but absolutely, I'm completely open to any ideas and to explore different things. Something that you should consider are the different mentorship programs you have out there. Womanium has a mentorship program. The Quantum Open Source Foundation has mentorship program. IBM has a mentorship program that you could explore. And yes, I'm open to collaborate, of course.
And for all these participants that again we watch the recording, what could be the best advice for Latin America? How to cool with the good the good advice on how to grow up like and create a quantum workforce in communities.
Um, there are several communities of Latin America coming here and there. My best advice for starting work growing the workforce would be start participating. So the summer school from I will tell you this. So all the people that I know from Latin America that works in quantum computing, I met them virtually at the first summer school that IBM did. That includes Alberto Maldonado, both Alejandros from Colombia, a lot of people that is around, and they are doing really serious research today. I met them in these schools when we started knowing zero about quantum computing. So it's a really really nice community. Everyone is nice, believe it or not. It sounds like a cliche, but it's true. So start participating in the events, and then you're going to start knowing people that has the same interest as you, and you're going to start learning and growing in the area.
Thank you so much, Daniel. um, we have more questions for the public. You can raise your hands and like you also unmute yourself and make the question directly for the speaker. Let's check it on the chat. Here's no more questions. Okay, it looks like there's no more questions. uh, Daniel, thank you for your time. Thank you for accepting the invitation for share your knowledge in our group, especially in this Kiskifal Fest that we make it for all the Latin America community and Mexico as well. Um, thank you too much. Thank you for your time and thank you for the wonderful conversation that we had today.
Thank you very much for the invitation, and let's keep in touch, and let's see what we can build out of this Cricket Fall Fest.
Thank you,
Thank
Dr.
you.
Sierra.